Good morning. I'm very honored and very pleased to be the first speaker in this colloquium, and I thank Professor Boissonnat and the Collège de France for giving me the opportunity. I'm very honored because of the prestige of this institution, and I'm very pleased because it gives me a chance of revisiting Paris. That is a very desirable destination for a lot of people to visit. And the talk that I'm going to give has no real technical content. That is, technical content is for me a thing of the past. Every moment in life has its own profile, and especially for people on Sunset Boulevard like me, okay, I mean, it's time then to reflect a little bit and to give some history. It has also no pretense of being a contribution to the history of computer science, because I'm not a historian by profession, and because I'm just here to give you some personal reminiscences of my experience in this field, and to try to describe to you what was the intellectual atmosphere, the intellectual situation in which computational geometry developed almost half a century ago. In the early 60s, I'm speaking of the early 70s, and computer science had been active, had been recognized for maybe 10 years at that time, and it was established, but it was a very green discipline in the early 70s. It was a green discipline because it had established its name only very recently. In fact, I mean, there was already an exuberant and enthusiastic scientific community, but it was under the tutelage of its natural mentors, that was mathematics and electrical engineering. Electrical engineering supplied the technology, and mathematics supplied the intellectual foundations. But at some point, this group asserted its own identity and looked for a name, and the name that came out was computer science. It's an interesting thing. I've heard that this name was not the final, I mean, it was a kind of default choice, because the first name being discussed, for what I hear, was really informatics. But the name of informatics was preempted by a copyrighted name of a small company that prevented anybody from using that name, but that folded shortly thereafter. So the name computer science was chosen, and other people, other groups in the world, in the non-English speaking world, were freed from that constraint, and they could choose a name that avoided the natural rivalry with engineering. It was informatics. So computer science came about, and came about in the early 60s, and that was the first computer science department that was established at that time. What happened in this year, the way that I recall it, in the mid-60s, I mean, the emphasis of computer science research was mostly in digital circuit design and in the development of the new programming languages. It was the time of Algol, of Pascal, and so on. And there was also a strong, an emerging interest in algorithm, but that, in my opinion, was not the main focus of the discipline at that time. And but in the transition from the 60s to the 70s, computer science really came of age. There were a few fundamental events or facts or contribution that established that. The first one, in my opinion, was the Stephen Cook distinction between the two classes of P and P. The algorithm, the problem whose solution can be easily computed, and the P class, and the problem whose solution can be easily verified, the NP class. And of course, I don't mention in the subsequent half century how much attention has been given to this problem and whether these two classes are distinct, and maybe maybe the answer will never come. In any way, another very fundamental contribution was the monumental work of Donald Knuth that gave rigor to the definition of algorithm and also to its analysis. The third very important contribution was the book of E.O. Hopcroft and Dolman that, beside many contributions of algorithmic nature, punctualizes the issue of the computing model. The computing model, which was the RAM, was the common abstraction of the practical totality of existing machine at that time, so that the cost of executing an algorithm was not related to the machine on which the execution was performed. It was a common abstraction of all of this machine, and they defined really a computational model. A computational model that was clean from any specific implementation, that had a stored program, a memory, a directly accessible memory, and where the units of, the operands were clearly defined as fixed length binary strings, and the quantification was expressed by some conventional cost of each individual operation. That enabled then the formulation of the analysis of algorithm by identifying and counting the occurrences of specific crucial operation, of course, to which everything else was proportionally linked. That gave origin to what is known as the asymptotic analysis, in which constants were ignored, and that was freeing the algorithm designer from incredible constraint, but also led in subsequent years to some undesirable excesses that were seriously criticized. So the machine that they formulated was the so-called RAM, random access machine, and it was basically the abstraction of the von Neumann machine. I should mention here that rather than just von Neumann, for historical correctness, it should be called the von Neumann-Eckert-Mockley machine, because it was that trio that really identified that machine. My interest in the field, and I apologize if some of the references that I make refer to my particular experience, my interest in the field was kind of fortuitous. I was spending a long leave at the University of Pisa in an attempt to return to my native country that didn't work out. And on that occasion, also Herbert Freeman from Radboud University was visiting the same department. And one evening, he suggested to Fabrizio Lucio and myself in a very light-hearted way, the following problem. It was called the floating currency problem. The floating currency problem was the problem of there is a place where everybody has a portfolio of foreign currencies, and this currency fluctuates every day. And periodically, the king or the mayor or the most important person is chosen as the one whose portfolio has the highest value. And the question was, well then, how can we identify a subset of the set of all the people of this place that are the only possible competitors for the title of king? And it was clear, since there was a natural partial order over the portfolios of these currencies, that this was a problem of finding the maxima of a partial order. And it was basically the maximum of the partial order. But the interesting thing for me was the fact that this problem could be formalized as a point in multidimensional space, as a collection of points in multidimensional space in which it was the partial order, and we have to find the maximum. And I found that the fact that the problem of this kind lent itself to a geometric formulation fascinating. Fascinating because analytic and projective geometry had been fascinating topics during the early years of my university studies. So I was convinced that then that, excuse me, that field was going to be an important part of my subsequent research. I must say that isolated algorithm of a geometric flavor had already appeared at that point, but they were isolated things. They were not part of a concerted effort to develop a new research area. They were isolated, they were not very elegant, they were not efficient, and so on, and they were mostly concerned with convex hull computations. For example, the gift wrapping approach of Jarvis to computing the convex hull. And but then at that point, a very important paper appeared by Ronald Graham. It was a convex hull algorithm that did not indulge in the errors of his predecessor and clearly isolated during the computation items that certainly could be excluded from belonging to the final solution. It was therefore a combination of algorithmic efficiency and aesthetic elegance, and it must be said that aesthetic elegance has remained a defining feature, in my opinion, of the development of this field. In other words, people involved in computational geometry were involved also in having beautiful algorithms. In the fall of 1974, when I was working with a young colleague, the late Sejun Hong, on these problems. We were tackling the problem of convex hull in 3 dimensions, and we were elated to find out that the convex hull in 3 dimensions had basically the same asymptotic complexity as the convex hull in 2 dimensions. And then we thought, naively perhaps, that perhaps this we could extend this then in the same way as the maxima of the set of points problem had been solved. But unfortunately, the complexity in 3 dimensions was just a lull in the complexity, because it turned out in higher complexity things changed dramatically. I may also say, for historical record and with no pretense of anything, that we landed at that time on the optimal construction of the Voronoi diagram, to find out that 2 months later that Shamos and Hui had published this among several other results at the Stock Conference of 1975. So, the contribution of Mike Shamos, beside the wealth of geometric results, was also the fact that he gave the name to the discipline. He coined the name computational geometry, and it's a name that half a century later almost has survived intact in the English-speaking world, not in France. And it was a small community, a small, enthusiastic, and very friendly community formed at that time. It was small. Besides Shamos and Hoy, it was David Topkin, Richard Lipton, and John Bentley, and a few others, and I cannot remember them all. But it was extremely friendly in the early exchange of results, and we met periodically at the at the important theoretical conference of computer science, Stock and Fox at that time. That became the constant venue for us. Immediately, though, there were some problems that had to be solved. I mean, the first problem to be solved was the model of computation. And the most attractive thing that existed there was already the RAM. But of course, as I already mentioned, the RAM had the feature that the operands were of fixed size, which in the numerical sense means that we can only deal with integers of bounded magnitude. And that is not really a model that is acceptable to geometry based on the Cartesian modelization. We need real numbers. Well, at that point, we felt that floating point knowledge and methodologies were enough developed, were enough mature, that we could take floating point as the machine to deal with real numbers. And so we invented at that time the real RAM, which was basically the standard RAM of Hopstad and Ullmann, extended with the capability of handling real numbers. It was a cavalier solution. It was a cavalier solution because it was comfortable. And I must say that it came with a double phase, a benign phase that was it opened, it freed the algorithm designer from the constraint of dealing with the numerical issues and concentrate on the geometric property. And in fact, the flourishing of computational geometry in the subsequent year was amazing. The malign phase is that a few years later, it was found that the model was insufficient because of the noisy nature of the comparison, which was basically comparison with zero, and floating point cannot really get down exactly to decide which side of the zero a comparison works. And in fact, there were provably optimal algorithms, especially here in France. I remember there was sufficient discussion at that time. Provably optimal algorithm led to flawed programs. The programs gave flawed results. And it is due to several members of this community, several years later, perhaps 1 or 2 decades later, to correct this insufficiency with a more profound definition of the model and with the strengthening of the model. Another issue that confronted us at that time was the formulation of which were, and I'm speaking of the 70s, okay, I'm speaking of 40 years ago, were the formulations of the paradigms, the computing paradigms. Of course, the most natural one was divide and conquer that we imported from other algorithmic development, in which we divide the problem into 2 subproblems, solve them, and combine the solution. And the other one, typically of geometry, was the plane space sweep, in which there is a linear variety, typically, that sweeps the space, leaving on one side the solved portion, and on the other side, the portion to be tackled. And the third one of these computing paradigms was the introduction and the use of duality. A duality of a two-dimensional algebraic variety with respect to a two-dimensional algebraic variety, either a conic or a quadric. That is a topic that was very dear to the minds of French mathematicians of the past centuries. And I must also mention before closing, and maybe I'm taking too much time, I will also mention before closing that that was the time of easy results. we were fortunate because we were at the beginning of the fields and we had all the easy problem, and we were producing one result after the other, but they were the easier problem. We left the tougher problems to the subsequent generation of researchers. And I'd like to conclude my few remarks with a few anecdotal facts. In 1979, I was spending a sabbatical leave at Erie at Rocancourt, and I had a lot of contact with French informaticians at that time, or mathematicians, they were mostly. And that were, for whom computational geometry was an unknown item. And in fact, even the word computation was not really acceptable in the French language as a cognate word, as a cognate Latinate word. And in fact, it took some time for them to develop the word, or to propose the word algorithmic, that is really even a more appropriate definition of the field, I must say. And another thing that I would like to mention is that my good friend and colleague Jean Wimmer arranged for me a meeting one evening with a young fellow that was a cousin of his spouse and who was a student of computer science in a French university. So we met in Rocancourt at the corner bar in a windy and rainy evening, and we discussed things, and I tried to impress to him that computational geometry was going to be a blossoming field in the subsequent year, and in fact, I was right. The name of that young fellow was Bernard Chazelle, and in a few years, he became one of the most productive contributors to the field, and I'm very pleased to say that he will be the next speaker in this colloque. Thank you very much.